Can you explain the basics of photonic quantum computers for like a high school or maybe early college level?
Yes, absolutely. So, photonic quantum computing is basically what we do is we take individual particles of light called photons. So these are what the world is made up of. When you turn off your flashlight or turn on the light, there's lots of photons coming out. And we at Quandela, or for photonic quantum computing, are able to separate these huge amount of photons which come out of a flashlight and only generate individual photons. And then with these individual photons, we can do computation because photons are what is called quantum particles, and these quantum particles they behave differently to the everyday behavior what we are used to. And so, if I give you an analogy of generally how this difference can maybe bring some advantage, is if you imagine you have a classical normal particle, let's say what we're used to, let's say a football, or you have a photon, a quantum particle, and let's say these are now doing a race. They are going to race a certain racetrack, and we want to see who's faster. And now we have to be aware that the photon, the quantum particle, is different and therefore has some extra properties. And I'm just gonna call these extra properties now wings. So let's say the photon has wings. And now if we do a race, let's say we have some obstacles in the way. Let's say we are doing a race and there's like a big wall where if you don't have wings, you just have to walk around. So you have to go like a detour around the wall. Whereas if you have wings, like the quantum particle, like the photon, then you can just fly straight over it. And therefore, you have a much shorter path, and you're basically taking a shortcut in the race. And of course, that will enable you to win the race, and therefore, you're much faster. And this difference in quantum particles and classical particles allows quantum computers to be faster in certain scenarios. And in photonic quantum computing, it just means that we're using photons as these quantum particles, whereas one could also use other things. Yeah.
Makes sense. So I did some research. I thought I knew what photonic quantum computers were, but like the more I looked into it, the more there was like a rabbit hole. Like it started like branching off in like different types, squeezed light versus like single photon, and how you encoded the information into like what part of because like I thought of photons as like okay, they have polarization and they have like frequency, but no, like apparently there's more things to them and um, so I guess to start to understand how Quandela does this, do you guys do squeezed light photon computer or quantum computers, or do you guys do like single photon quantum computers?
Yeah, very, very good question. And here in Quadella, we're using single photons, so we don't use squeezed light. Um, and that means we are really focused on, as I mentioned before, generating individual photons and then manipulating these photons individually. And here we can still use the different types of different properties of these photons. So you mentioned already we could encode information in the polarization of individual photons, which would then act as like a two-level system if you have two different types of polarization. Or we could use a spatial differentiation. So basically, what we do is we place the photon in two different physical locations, physical waveguides, they are called, or you can think of them as optical fiber, similar to what you have for your internet. And basically, depending where physically the photon is, this is our two-level system. And and then this is basically a second way of using it, and this is the main, the main way of how we use photons. But we actually do both.
And it sounds like because this is quantum, it the photon would kind of take both paths at the same time. Is that accurate?
Yes. So initially, the photon we place it in one of the two possible arms or possible waveguides. But then, in the interaction in the photonic chip inside of our quantum computer, the photon will um, travel through the optical fibers and then um, turn into a superposition. So this is one of the special properties of quantum particles in general and also photons. And superposition means that it takes on multiple options at the same time. And this is exactly what you referred to. It will be in multiple positions in this case at the same time until we measure it. So it's a new state of being which does not exist in our day-to-day life. And this is exactly what one of the wings I referred to in the beginning.
It's cool. So tricky question. I don't know how you would answer it without like a bunch of diagrams and stuff, but I'm gonna ask it anyways. So this sounds like um, if I have a certain algorithm that I want run, it's almost like the circuit already has to be there for it because like you already have to have it. Okay, so for example, if I was doing like a neutral atom quantum computer, if I think of a new circuit, I can just like move I can use the lasers to move the Rydberg atoms closer to each other and like move them around and all that stuff. But it sounds like for photon computers, it like already has to be set up in a certain way. Is that correct? Or do you have like a way to make it malleable?
Yes, that's a very good point. So the circuit structure itself is fixed. So we produce one photonic chip and then we place it into the quantum computer and we're not changing the physical structure of the chip. But inside the chip, there are different optical components which basically are the gates of the photonic quantum computer. And one of these is a phase shifter. And basically, what a phase shifter does is when a photon travels through the phase shifter, it changes the phase of that photon. And the phase, if you think about a photon being a wave, it's just displacing the wave slightly. So it's not changing the wavelength or anything, it's just changing the position of where the wave starts. And these phase shifters, they are actually tunable. So even though the chip itself is fixed, we can physically from the outside change the values of these phase shifters of how much they change the phase. And this is then how we can program different algorithms on the same chip.
Interesting. So I guess the you would have like let's say you had two entangled photons coming in together. You could change like how they interact with each other by what phase you had given them beforehand, kind of.
Absolutely. And we can, and actually in the chip, there's multiple of these phase shifters which we can change. In each of them, we can change differently so that basically the photons travel through the chip and are in a quantum superposition and interfere with each other. And depending on how we tune the phases, we get different outcomes of the final quantum state, and therefore we can basically encode any type of quantum algorithm.
That's really cool. What so do you work on the hardware side, the software side? I guess what's your specialization?
Yes, I'm more on the software side.
Okay.
So I love doing a tour in our hardware factory and labs and get explained how everything works. But myself, I'm not in the hardware team directly, and so I've started working at Quandela in the applications team, where we develop algorithms for direct user applications and where we work with external clients to build applications and algorithms for the use cases of the clients so that in the end it's cool to build a quantum computer, but only if we can actually use it. And so the aim of my work there was to make and find useful applications for quantum computing. And in the last year, I've transitioned a little bit. So now I'm not actively programming our quantum computer and developing algorithms myself anymore, but I'm now bridging the gap between the users and the developers to find out what other projects we can work on together and to explain and to basically be the be the bridge between the really technical part and also the more business orientated part to translate between the two.
So that seems to be like the big question that I keep seeing in quantum computing is how can it be applied? Um, like it seems like a lot of the time it's mostly just applied as like a proof of principle, and like maybe in the next few years it'll be applied in a way that it can like pay for itself. You have, I guess, one, do you agree with that statement, or do you think we're a bit closer to it being applied in a way to itself? And I guess I'll hold my question until you answer that part.
No, I do agree with it. So right now, there's not yet any useful quantum computing. So we have a lot of, as you said, small applications, and we have quantum computing where you can test these out, but they are on a scale which is not yet practically relevant for any organization because you can simulate most quantum computers fully on a classical computer. And we are now just getting into the stage where we see the first experiments of quantum advantage, which means that we can do something with the quantum computers which classical computers cannot simulate. So this exists already. But right now, these quantum advantage examples do not fit any practical task. So this is the next step to become practically useful is that we have a practical task we solve using a quantum computer which cannot be simulated classically. And
Right.
specifically also that the task cannot be done classically any better, of course. And
Yeah.
we're not there yet, and it will definitely take a few more years. Of course, we never know, but uh, I think it will be like a very slow start in the beginning of we find first application for very specific topics where we have a tiny increase in performance due to a quantum computer, and then at some point it will go rapidly that as soon as we have quantum computers which easily perform quantum advantage, we will basically be able to apply them to a huge amount of use cases because use cases there are many. It's more the challenge to find the first use case which can be basically applied to the earliest quantum computers which are not yet like the most powerful ones.
Are you able to talk about any of the like any specific examples that you worked with? Any
Yeah,
companies? Any
absolutely.
problems?
Yeah. So one example I think I can share is we're working together with Orange. It's a French telecom company on the use case of malware detection.
Hmm.
So there we um, basically build a quantum classifier. So this is in the field of quantum machine learning, where the input, similar to any classical machine learning, would be an image, and then the quantum classifier would determine if this image corresponds to a malware or a normal data form or like a file. And this is something which we can do right now already. So we can work with real data from Orange to classify it into these two categories, and we get good results, but not yet on the scale where we can replace a classical computer. So right now, the size of the problem, the size of the picture, the images, and the number of images we can kind of work with is not yet outcompeting the classical solutions. But basically, if there wouldn't be the classical computers, which are already super advanced since we have them for nearly 100 years or close to 80 years, then there would be some use for the quantum computers. But of course, we are competing with like a existing technology here, and so right now it makes more sense to use the classical computers for these tasks.
So let's say like it's 10 years from now and the photonic quantum computers have gotten a lot better. How would you say the quantum computer would be better than the regular computer for malware detection? Would it just like be faster? Would it be like more accurate? I guess is there a specific part of quantum that makes it, because like I guess maybe I just don't have the imagination for it, but I don't see how entanglement would help unless like maybe there's some sort of quantum entanglement machine learning algorithm that provides much more. like information capturing density within the same neural network? I don't know.
Yeah, so actually it's not far off. So there will be different possibilities of where quantum computers can bring an advantage, and of course I don't know which of these will be the ones most or like the fastest to evolve, but I can make some guess on that. And so one is that you will be able to um, build a machine learning algorithm and train it with much less data than you would need for a classical machine learning algorithm. And this is pretty much what you explained right now. We can already see that quantum computers can capture much more information with less trainable parameters than classical computers can. And so
Hmm.
once the quantum computers improve in performance, they will be able to use the same number of parameters as maybe the classical ones we have today, but then have a much better performance. Or you could think we could just have less of the classical capacity right now, but um, and therefore basically use less computing power for the same output. And so these are two very either we get like better performance or we get the same performance but with less resources. And the resources could be either the number of training data we need, or it could be much more specific on resource. It could be actually the energy cost. And this, I think, is a very important point, especially in machine learning. I mean, we know that right now we are getting in big trouble that because all the data centers are um, using all of our energy, and this will bite us in the ass, I think, very soon. So I think this is has a huge potential for quantum computers to have like one of the first useful impacts that just doing the same task but with less energy.
Yeah, I read in the United States, there's a state in Virginia where 25% of their power right now goes to data centers. So
Right.
yeah, it's starting to get, and people are going to start noticing their water bills and their electricity bills go up. So yeah, that's crazy. That's
Yeah.
interesting. So it's almost like entanglement gives you another dimension to learn data in.
Yeah, I think I would even say it's not necessarily just another dimension. It's just a different way of seeing the data. And therefore it can extract different information from the data. And in some cases, this different information means better information. And and also and that's what I think is where the first application will definitely be found is in combining the two. So it will not be a purely classical or purely quantum algorithm, but we would have a workflow where we take let's say an image and we feed it into a classical image classifier and a quantum image classifier, and then we take the output of both of them and combine basically the results to get our final output. And there, I think the gains of inaccuracy will be the highest because we can leverage what quantum computing can is good at, and we can leverage where classical computing is good at, because there's no reason we have to do everything with a quantum computer. And so having these like hybrid quantum classical machine learning models, I think this is really where we will find the first advantage, and this is then where this difference for in quantum computing really comes out.
Would you say that's where Quandela is going in the next 2 to 5 years? Is there anything else that you guys are tackling?
So that's definitely where we're going. So we have just launched a new hybrid quantum AI software called Merlin, and this which does exactly that, which allows classical AI researchers without having to know anything about quantum computing to build their classical pipeline using well-known Python libraries for machine learning and then insert quantum machine learning aspects of it to build these hybrid models. And we've basically abstracted away all the quantum information parts so that for a non-quantum expert, they can still use quantum machine learning in their classical machine learning models. And we believe that with this approach, we can expand the reach of users and developers looking into applications for quantum machine learning, and that this will inevitably bring basically some useful applications for quantum computing in these hybrid architectures just by trial and error by a huge number of people, because then we will be able to find the specific data set, the specific problem where this combination of quantum and classical has the most effect and therefore can be used the earliest on as soon as basically we have um, just enough power of our quantum computers. And then later on, it will obviously expand.
So is Merlin, and hopefully I'm pronouncing it the American way, I guess.
That's
Is
okay.
that like, so I read you guys had something called Percival. Is Merlin like the next version of Percival, or is that something entirely different?
So there's two separate things. Maybe just to
Yeah.
give a quick overview because I'm sure the the listeners will not know what these two terms mean. So as part of uh, our mission to make quantum computing accessible, we of course not just build the machines, but we also build the software to use the machine. And so Percival is the first open source Python framework which we have developed and which is available to program directly on our quantum computers, on these photonic chips, and also to simulate them. So Percival is very specific for photonic quantum computing for our machines, and it exists and it's still in use and will always be in use. And now Merlin is a new Python library separate to Percival, which we have developed, which is one level of abstraction above, where you do not anymore need to program the exact quantum circuits, but you can um, take basically predefined quantum layers and insert them in classical PyTorch, for example, PyTorch environments. And so it's a separate thing, which is also open source, but it has a very different target audience, and it will allow the quantum developers or the quantum algorithm developers to work much faster and trying out different algorithms much faster. And it's in the background of Merlin. Percival is still connected, but you don't see it a lot in Merlin yourself. So you don't need to understand how Percival work in order to use Merlin.
You mentioned PyTorch. Is it because you're using like the matrix handling abilities of PyTorch, or because you're doing you're almost like getting ready to do AI stuff with PyTorch?
Yes, so we use PyTorch to do AI. We don't use
Oh,
PyTorch
okay.
any. So it's really to basically, if I want to build a image classifier, let's say for our example with Orange on the malware classification, then I could build my own quantum classifier and just try this and then see my results. But if I want now to combine that with classical machine learning algorithms, I would have to somehow combine them together and write some like code on how to like connect the two. And so with Merlin, this work is basically done. And what we provide is within the existing PyTorch structure of you build different types of machine learning layers. They could be neural networks, they could be fully connected. You can choose different types of like machine learning uh, capabilities classically. And now you just have with Merlin a possibility to just insert a quantum layer within the existing PyTorch syntax. So you don't need to learn a new syntax because this is, of course, another issue in the quantum world that you have 1,000 different software kits and everyone works
Yeah.
slightly different. And so with Merlin, you do not have to learn something new. You just need to know how PyTorch works. But okay, I think this is something which much more people already know. And then you can just say instead of I want to add a neural network, you just said I want to add a quantum layer. And then you just do that. And inside that quantum layer, in the background, Percival makes sure it creates the right circuit for you and inserts the photon and runs the simulation and all of that. Or if you want, runs it on the quantum computer directly.
Really cool.
Yes.
So last question. In like at least in my experience, uh, I'm starting to get old. I'm almost 40. It's been a challenge to get like I've always wanted to be working in quantum space, but it's been a challenge to do it. I was wondering if you'd be willing to share with us how you got into Quandela. You were saying that you started out in Quandela as an applications engineer, and now you moved into more software side. Um, where were you before that, and how'd you get to Quandela?
Yeah, so actually for me it was a Quandela was the start of my quantum experience. So I did not do any quantum computing beforehand, and I studied mathematics and physics in Scotland, and then after I finished my master, I didn't really know exactly what I wanted to do, so I just like looked around what fields there are which maybe are slightly related to my degree. And so I've heard, of course, the term quantum computing before, but I didn't have like specialized courses on it. I didn't do like a master specific in quantum computing at the time. That was not really a thing that's now popping up. But
Can I
and
ask,
so,
sorry,
yeah.
can I ask what was your master's thesis about?
My master thesis was in physics about quantum chromodynamics.
Okay. Yeah.
So
So
it
something
has the
quantum
word
related,
quantum in
basically.
it,
Yeah.
but it's completely unrelated to quantum computing.
Yeah, it's more
It's
like field theory and yeah.
exactly, it's theoretical physics. Yes.
Okay, sorry to interrupt. Continue.
No, thanks. And yeah, so and then I just honestly I just Googled quantum computing startup, and I didn't have much hopes, but I thought this might be a cool way of staying with science without having to go to academia. And then I started to find a lot of startups actually. And I was looking mainly in Europe, and there were many, and Quandela was one of them. And I just applied. And I was lucky that at the time I was applying, Quandela was expanding the application team, and I was looking for basically junior roles. And so it was enough that I studied physics. That was a requirement. And then I started there, and I would say in the first year at Quandela I learned so much, not just about Quandela's technology, but also about the global space of quantum computing itself. I went to some conferences and got like put in touch with like all these other different technologies, and it's now starting to get to a point where I'm like, okay, I've got a base. I know kind of my way around, but I mean, I'm still, of course, learning every day. But yeah, so it was a bit by chance that I got into quantum computing. But it's I'm very happy I I found this. Yeah.
Is the software engineering part because so again, my personal experience, they teach us all sorts of different physics, but they don't teach us like how to be software engineers. Is that something that you've also found like been one of the harder parts of this job?
Yeah, absolutely. So in my physics degree, we had like some courses on Python, but very basic. And so when I started Quandela, that was definitely one of the things which I had to like learn the most, to program and to actually build algorithms, and even like how to use GitHub and like Git.
Yeah,
And I was
Jira,
like, I don't know what this
Jenkins,
is.
being part
Um,
of a whole team. Yeah.
Yeah, exactly. And so this is definitely something which was one of the biggest challenges for me coming from the physics side. But then there's other people who came from the software engineering side or from computer science, who, of course, for them, I guess the physics part and learning about what quantum mechanics actually is was more the harder part. So it's depending, of course, what your background is. Um,
Yeah.
and but yeah, so that was super interesting. And now that I've moved a bit away from that, I'm of course not programming as much anymore. So I'm improving less, but I'm still using what I've learned in the beginning. Yeah.
Cool. So Samuel Horsch, hopefully I pronounced that correctly.
Yes.
At Quandela, I think that one's a bit easier to pronounce. Thank you
Yeah.
for taking the time to talk to us, and yeah, good luck.
Thanks a lot.